Okay, so up to this point, we had began by, I should say this section, we had cracked open those clams, which are in which phylum? So one of you is right, one of you is wrong. Yes, because it's the phylum Mollusca, and it's the class Bivalvia. Okay, what's another class that we have discussed? And what's significant about gastropods? An animal. Say that again. Snail, slugs. So why is it that those animals belong in that class, gastropods? Well, there's a couple of reasons. One, they're slow, they'll produce slime. But what we had mentioned, when I say spent the most time in trying to discuss, is when it comes to digestion. It's rather unique to this class of gastropods that they do this process. And we tried to illustrate by me, if I don't hurt myself, trying to twist around and crack, 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 crack. Okay, yep, we're better now. Okay. Yeah, so their internal mantle cavity is going to rotate 180 degrees. And the reason it does that is it lengthens the intestine for more area or more length for nutrients to be absorbed there. Okay, then going back to our original question, how much money is 6 bits? No. We've heard so many, 75 cents, because it's 2 bits, 4 bits, 6 bits, $1. All want to learn about bivalves. Stand up and holler!
Is this recorded? Yes.
What difference does that make?
So I can go back and watch it.
Why would you do that? Look at that idiot make a fool of himself.
No, what if I'm having a bad day and I want to laugh?
Oh.
Not that I'm laughing at you.
No, I understand that, because who else? Of course I look like an idiot doing that, because I get paid to do that. Just like everything we talked about, those gastropods, those bivalves, maybe we're just making that up.
Probably are.
See, you don't know that. So what's the significance of that mouth on a bivalve being on the anterior side? What's the significance of that? Nothing, but you didn't know that. See how you can kind of do that? Yeah. See, we get paid to look like a fool. Yeah. Okay, I think the computer, yes, here we go. Okay, so our gastropods then, okay? As we know, are slugs and snails. Now, one of the things that this is probably the start of these animals becoming more complex. Not just because we told you, but when you look at this, why would we say these animals are becoming more complex? Okay, they have these eyes, which we consider tactile organs, and did he land on me? These flies, I tell you, don't land on my coffee. I didn't see where he went. Oh, I could have swatted myself then. Dang it. Because I want to say that's the last one we have to go through. Okay, so not only these tactile organs, but look at what we see here. In order to be able to move from one place to another, yes, we have jellyfish that could do that. You had Medusa that could do that. And what would happen is water comes into this specific structure in a jellyfish in a manubrium, and that was called what? I'll try to. So yes. So then when this, boy, I know I can't do it. I'm not that coordinated. But then that velum will contract and will allow water to be pushed out behind it so it can move in that direction. Okay. So that's where we saw movement start to take place, but not nearly this advanced, because now you have, when we're talking about predation, it's easy predation for the cnidarians. Why would that be? Why is predation so simple for them? Because it's one of the characteristics that those animals belong in that phylum. And that is what? Because you're going to hit yourself over the head and say, I knew that. It's not their symmetry. Again, one chapter back in the cnidarians. Okay, so what's significant about their tentacles? Now you're really, really close. Okay, yes, in their cnidocytes they produce venom, so that would make predation very easy, and that venom is probably tailored to whatever it is their prey item would be. Okay, so moving on to class Bivalvia. Okay, so we had seen these animals up close yesterday. So it says depends upon ciliary currents, okay? That's just a fancy way of saying water currents, and we'll explain why that is in just a moment. Okay, so we have our handy dandy clam stand-in, or example. Did you get him? I take it you swatted a fly. Oh. Okay. Did you throw your pen at it?
Yeah, she did.
Oh. Oh. I thought maybe you were
It was like trying to
shaking
hit
your
my
pen or
ear.
something and it flew out of your hand.
I
Okay.
know it was like buzzing her ear. So it just. Yeah, it was just buzzing. So was that my pen you just dropped on the floor? No.
You could have poked her in the eye.
It's a bugging.
Oh, see, I'm detecting movement. You went like that. I thought you were pointing at it. Okay, darn fly. Here's our stand-in for. Oh, geez. I didn't mean to do that. Okay. Well, this might actually work even better then. Okay. So here's our. I probably can't see anything because it's such a bright background. Okay. So then, what we see here, it said it's laterally compressed. There's 4 sides to these animals. Okay. Where the mouth and head foot is, that's the anterior side. Okay? So then what's opposite the anterior side? Say that again. Posterior. Then you also have the front side, okay? Because remember they're laterally compressed. So would that be dorsal or ventral on the front? Oh boy, our medical terminology coming full circle, you two. Sure? Yes, that's true. The front would be the ventral side and the back is the dorsal side. So when we say that they're laterally compressed and that hinge ligament, well, I guess it's a little sticky. just the idea that holds that shut, that hinge ligament. It's on the dorsal side. It's underneath, inside the mantle cavity, but it's on the dorsal side. And there's a little bump there that went across, how do I want to say that? When you look at those clams, okay? Oh boy. Kind of looked like that. There's a little bump perhaps right up here. That structure is called the umbo, and that is where that structure will be found, that hinge ligament. We okay? Or is it just my drawing that looks so good that, oh, okay. Okay, very good. Okay, so as we said, they're laterally compressed, that hinge ligament, which is on the dorsal side. Holds it together dorsally. Okay. Then, shoot, I got it wrong. It's actually on the front side. I put it on the back side, okay? So here is what we're talking about here. We have, it holds it together on the dorsal side. It's just referring to where it's at. So that, what are these two structures right here trying to elude you to? And you actually saw it on the outside of the mantle. I think it was this one. It was a black spot. Yep.
You said it yesterday.
I know, and I said for those of you who have had anatomy and physiology, the difference between this type of muscle and this type of muscle. Okay? Is this one an abductor muscle? No, it's not. It's what's the opposite of abduction. No, not that. Say that again. Because I don't think you said it correct. That's why.
It's like ABD and then it's AB something.
No. The opposite, abduction, means it's going away from the midline, but bringing it closer towards the midline is adduction. Please tell me that's what you said. Just lie to me.
No, I didn't say
You did? Okay, that's what I thought. Okay. See, I'm not getting old and senile yet. Okay. Those are their adductor muscles. And it might have even said that on your paper had we looked a little further down the line. And oddly enough, I believe it is starfish or echinoderms. Echinoderms are a different phylum that would include your starfish that actually prey upon these animals. So probably what had happened is as these animals developed, the ability to, let's say, keep their mantle closed would be certainly a structural adaptation that it would help them not only just evade predators, but protect their internal organs. Looking at the floor. I missed.
There's two of them over there.
See, I think you're saying that every time. I actually hit it, and there's actually two of them, and you tell me I miss.
Well, tell me where it went then.
Well, sometimes you. Where?
Flying over there now.
Yeah.
I just saw it right.
Oh, right here. It's gonna go in my hair.
Now you're just having me walk from one. I did see it over there.
It's on my tube, right beside me.
Boy, I'm getting my exercise today.
Oh, get it by your board now.
I don't think I got it. Because I didn't see it fall down. It is getting to be that time of year. They get to be really, really pesky just because it's getting colder. So they try to hover around warm areas, your face, your skin, anything that gives off warmth, and that's why they get to be so annoying. So, yeah. I would spray some pesticide in here. It's supposed to get rid of pests, but you people would stay in here. You know, just paying attention. Okay, let's see once. All right. Okay. Then I want to do this one. This one. Because that feeding and digestion, I want to get started on that. Okay.
Right on the table behind that one.
Jeez.
Well, you got to swat with some major acceleration on that. Lucky it didn't, maybe, at least it didn't land in your bag. Okay?
Can you eat that one?
I'll do the next one.
What? No.
Oh, okay.
Your friend did the first one, so you can just do this one.
Nah, I think I'm good. I'll pass. Yeah. I just ruined the party. Dang it. Okay. So then, when we talk about the dorsal midline, of course, that is, okay, that would be where it's open. See, I got to think about this. What's thrown? There we go. It would be actually back here. I'm opening it like this instead. Okay. So when we're talking about these in-current, ex-current openings, we're referring to this, okay? This is where water is drawn in. This is the in-current openings, okay? And then this would be the ex-current here. Now, the reason for this is, I think we've only said it, clams are what type of feeders? They're filter feeders, because what happens is water and debris will come in through this opening, and it's actually on these gills then where mucus is secreted, and it will trap those materials. Okay? So that's what we're talking about, these in-current and ex-current openings in these animals. Okay? Now, this, you students were asking, what are these things sticking out of this mantle here? And it was this cilia that we see here, okay, that will actually not only just sweep these to the mouth, but they get trapped on there. Okay? It makes reference to what's inside the body and mantle. We'll talk about it a little more in depth here in just a moment. Nothing to right here? Okay. Now, remember, what type of circulation are we talking about these animals? Is it pressurized or not pressurized?
Not pressurized.
You're correct. It's not pressurized. So is that open or closed? Yeah, it's open, because what happens is, notice it says blood is pumped into the foot, causing it to swell, just like what we would expect that anywhere in the body, when it starts to fill with blood, then it's just going to swell and get bigger. And then what happens is, as that foot that's swelling and getting bigger, once that contracts, that forces that blood back into circulation then. Is it that big of a deal if blood goes backwards in their circulatory system, do you think? No, it's not, because this is a type of single circulatory loop. In other words, the oxygen is drawn out of the blood through diffusion. It's once you get a double circulatory loop, which means you're getting a little past the first set of vertebrates, which were fish, which will still begin to grab grab oxygen out of the water. It's not until you get to the very first tetrapods. So from biology, and what I want to say, that before the Dinosaurs project that you all had completed, what were the first types of animals that went from water onto land? Yes, they're called tetrapods, but can you be a little more specific? It was called a hynerpeton, if that helps. Nope, because they're reptiles. You're too far down the line. I mean, but they are tetrapods too. So it's something between the fish and the reptiles. You would think so, but those were arthropods. Yes, the amphibians were the first ones to make movement onto land because it would be the Petrolacosaurus, I think, was the little lizard-like animal that would just run around like this. It had its limbs going in every direction like this, and their flexible backbone, that was part of the things that allowed them to be successful then as well. You agree, Petrolacosaurus?
Yeah, I remember some of it now.
Yes. See? We're not just making this stuff up as we go. Okay, let's see here. Where does that put? Okay, so the feeding, I want to get through. I was going to say, we got to be getting close to the cephalopods. Okay, I want to try to get through the feeding here. Then tomorrow we'll finish the bivalves, and then next week we will get on to the cephalopods. And I think that dissection with the squid is perhaps a little more beneficial just because the animal is a little bigger. And for those of you who have done cats, it's kind of a little tricky when you say if the animal's bigger, sometimes that's better with the muscular, I want to say, not structure, but definition. Sometimes that's hit or miss because even though the animal's bigger, there can be more fat tissue on them that makes it a little more difficult to remove that so you can actually dissect the muscles. Okay. Now, on this next slide, there's something that I'm going to want to read upon because I don't think it's correct. Okay? Because I think the type of digestion should be different. Does everyone have this information that wants it? Okay. So then while you're doing that, I'm going to take a look at this. Actually, that is correct, but it's not for the reason that you might think. Because one of the things that we talked about yesterday and observed, what does that mean to you? That it actually takes place inside of each of its cells. Now, to me, this would be a transition between animals that digest materials intracellularly, and then those that digest extracellularly. And we'll make sense of that in just a moment. Does everyone have this content that wants it? Okay? And the reason, okay, so the author does say intracellular digestion. I think this is why we would call it an intermediate form. In other words, it never came up before the dinosaurs, but there used to be flying reptiles, okay? So the reason that is significant is that for anyone who's ever seen the Jurassic Park, the original movie, that's probably more widely popular than the Jurassic World, although I think they're both good for their separate reasons. But with Jurassic Park, they talk about how the Archaeopteryx is the animal, or they illustrate that animals like those used to fly, some of the reptiles. So that would be a link between animals that were found on the ground and animals that could take to the air. So who would come after the reptiles then? Yeah, the class Aves, or birds. So what we mean by this then, being in between that of, I'm just looking at the time, I try to be conscious of that, is that when we see this, okay, even though this has an intestine, to me, I think it makes the most sense that animals that digest materials intracellularly just keep it local. So this has intracellular digestion too. But when we look at an intestine, and to me this has a little more complexity to it, the idea behind that is we would think of extracellular digestion. But if things are broken down in the intestine and absorbed, which is true, what is it that needs metabolic activities all the time? Besides your heart, okay, your diaphragm, we would say for mammals and humans, but these animals don't have that. So even though this is broken down in this digestive gland, okay, intracellularly, these components are then sent into this intestine, but of all of these structures here, what would possibly need the most metabolic activities? When you look at here, this is a tough question. So it would be movement. You might think the heart, but okay, that's not that complex back here. Okay, so would it be this muscle, or this one down here? What would need the most nutrients, do you think? Why? But I mean, I would believe that you're right, but why would you be right? So bigger, I really never thought of that. That's true too. That's probably a good reason. But remember, the majority of time, these animals lay laterally compressed. So it's not that those muscles are flexing to keep themselves shut, probably if there was predation taking place. But when these are just slowly moving along, we said this muscle right here. But what's the name of that muscle? The head foot. So then what is actually inside of that head foot? We only talked about it, I think. I think it was wrote down too. Because the head portion means there's what inside of here? Starts with a G. Ganglia, which means what? What type of tissue? Nervous tissue, okay? Then why is it called the foot afterwards? The last thing you said, I didn't quite hear that. Yeah, so it'd be locomotion. We attribute the foot as walking along. So therefore, I think what would make the most sense when we interpret this, if this was going to be extracellular digestion, which I would think would make the most sense, even though it's intracellular here, notice these materials are going to move out of here, and this is so close to that area, it's probably going to deliver nutrients to here. So I think it's kind of a mix between that intracellular and extracellular digestion. Although the author doesn't say that, but I think that's a fairly decent intuitive leap that would say this needs the most nutrients, and then look at where your intestines are, right next to it. Okay, so that's where we're going to stop for today. So we will finish the feeding. We'll explain that a little more in depth tomorrow with the bivalves, and then we'll get on to the cephalopods next week. So signing off. Beep, boop, 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 boop. Next time. Is that a beatbox outro? Yeah, we probably could, but we'll save that for another time. Oh, okay. Thank you. Next time.